Welcome back. So in the course so far, we have dealt entirely with the dynamics of a single particle, single quantum mechanical particle, either propagating freely or interacting with some kind of potential. Now, it should be noted that when I mean by single particle, in physics, there is no distinction between a bunch of particles that do not interact among themselves and a single particle. Because basically that is a single particle problem repeated many times. So if I have non-interacting particles, then clearly each one doesn't care less about what its neighbor is doing. So the wave function of this particle is not dependent on any of the properties, any of the quantum numbers of the particles that surround it. So when I mean that we're going to go into multi-particle systems, of course, in the end, what I think should be clear to everyone is that what really makes a system a multi-particle, truly multi-particle system, is the presence of mutual interaction. So to put all these ideas in math, what we're going to begin doing today is discussing what in physics is called the quantum many-body problem. So a quantum many-body problem is a problem involving degrees of freedom associated with different particles. So here I'm drawing in the picture different particles. They could be identical or they could be distinguishable. For instance, two electrons are identical particles because in physics, in quantum mechanics, what characterizes these particles is their mass and spin and charge. And if you have two electrons, they have the same mass, the same spin, and the same charge. Well, of course, I'm talking about the S in the quantum number. So there is no way you can distinguish two elementary particles. You cannot tag them and say, this is electron John and that is electron Mary, because John and Mary, the person John and the person Mary have distinctive features. So, take a picture and you say, oh, this is John and this is Mary. And even if they are twins, you can always, go and find some small details that distinguishes them. For example, the behavior. While elementary particles do not behave like that, when they have all the quantum numbers identical, they are completely indistinguishable. But there could also be some distinguishable particle. For instance, here I'm drawing this particle with a different color. And by drawing by the different colors, I mean that they have different quantum numbers. Different mass, different charge, spin. However, on the other hand, position is not an intrinsic quantum number of the particle. An electron in this position or in that position is still an electron. It's just in different position. Because I can change the position of the electron, but I cannot change the charge of an electron and having the electron remain an electron, clearly, right? So the quantum many-body problem is a problem of a system of distinguishable or indistinguishable or mixed, some distinguishable, some not particles. So, if I were to write the wave function of this system, it's going to contain multiple entries. It's going to have the position of the first particle and maybe the spin of the first particle, the mass, which, let me put all the quantum numbers of the first particle in a vector n. And the vector n might contain, I don't know, the spin, the mass, the charge, and possibly other quantum numbers that the electron is, maybe the principal quantum number, the orbital momentum quantum numbers, whatever specifies the states of the particle. But also I have the same for the second particle. and so on, until you have the nth particle. Now, clearly, the wave function now contains a large number of entries. And this feature here is a really, really, really key point of quantum mechanics. You see how many states there are for a quantum many problem. You know, I'm going to be more specific. Suppose that, you know, my quantum many-body problem is only, let's take the simple system. These are just spin 1/2, so spin 1/2 particle fixed in a point. This is the smallest, the simplest possible quantum mechanical many-body problem, because you remember, if the electrons, for instance, are fixed in a point, then there's no degree of freedom associated with position, and all I have is to specify the quantum state of the spin. So I have only a two-dimensional vector space for each particle, right? So this can be plus minus 1/2, and that's it. This can be plus minus 1/2. This can be plus minus 1/2. So in this very simple case, the wave function is just a collection of spin, a probability to have any of this configuration. Right? So for example, the probability of observing up, down, down, blah, 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 a certain combination is given by the square modulus of the wave function of up, down, down, up, down. And you know, by this simple rule that we already have observed, we can reconstruct all the probabilities. However, even for such extremely simple system, even for such trivial system, to say, in the sense that it is really like for each particle I have the smallest Hilbert space, so this is really the, from the mathematical point of view, the least complicated quantum many problem you can think of. You need to specify a gigantic number of entries of the wave function in order to completely solve the theory. What do I mean? Remember, when we were looking at the particle in a box or a wave function for a single particle, we were saying, you know, a wave function is a collection of points, and it's basically a way of associating an amplitude psi to each of the points, right? So if I have n mesh points, and my quantum state is specified by n numbers, which corresponds to the quantum wave function in each of the points. Now, if I have a quantum many-body problem, even the simplest one, how many numbers do I need to specify? Well, clearly, for each combination, say I'm gonna just draw two combinations in which I only flip the first, for instance, just for simplicity. You see, all I did was to flip this, just to make this wave function associated with a slightly different quantum state. Well, for each of these combinations, I need to specify one number. And how many there are of such combinations? Well, for such a system, such a simple system, I have two combinations for each side. So I have 2 to the n numbers to specify to get the wave function defined. And the point that I want to emphasize is that this quantity grows exponentially. And if I have more than two quantum numbers, for instance, you know, I've also, I don't know, orbital angular momentum in each position. Suppose I have A quantum numbers, with A greater than 2, A possible states in each of these slots, then I have A to the n, growing exponentially even faster. So the big problem, so there's a huge gap in difficulties in going from one problem to a many-body problem, because the numbers, the amount of numbers you have to specify in order to define even just one quantum state, not to mention to solve for all quantum states, just to specify a quantum state, is growing exponentially with the number of particles. This is the quantum course. I don't know how to spell curse. I think it's curse of dimensionality. And so it really seems that solving quantum many-body problems is really strongly intertwined with the problem of beating the quantum curse of dimensionality. And this consideration will lead us towards some ideas that are at the basis of all the methods to solve quantum many-body systems. Clearly, the first thing you want to deal with it is this, right? Because even writing on a computer, even having sufficient memory to write down the possible quantum states, not to mention to solve for them, can very easily, can very rapidly exceed the memory of your computer. So how do we deal with that? Well, there are historical ways to do with that, and there are modern ways to do that. I would say the traditional way to deal with this problem is to try to somehow do as much as possible to reduce this problem in order to make it look like a single particle problem. And I will discuss about that in the end of the course. Try to perhaps get in some partial information, but reducing the problem to a form that is dimensionally tractable. The other strategy is very modern, and I will not touch on that, but just to mention the name, is to use sophisticated recent techniques that allow you to concentrate only on the states that are really relevant, rather than dealing with all the states, which are too many. In the end of the day, maybe the system never visits some of them. For instance, just as an analogy, I have a wave function, and the wave function is strongly concentrated in this point. There's no point of putting mesh points here, 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 if the function is 0 here, right? All you need to do is to put points where the function is actually not 0. So by the same analogy, there are many of these quantum combinations of spin up and down, for instance, that maybe in some physical system are never visited. And a big line of research that is going on these days are called tensor networks. And this is, if you want, outside the course. I'm not going to ask you about tensor networks in the course. I just want to put there a keyword that you might hear if you Google quantum many-body, or this is one of those keywords such as AI, artificial intelligence, that is very popular these days. And so tensor networks are precisely ways to represent quantum wave function in a low-dimensional fashion by retaining only the relevant parts of the quantum wave function. The other big line of development to deal with the quantum dynamics is to use quantum computer to solve quantum problems. So computing in which, rather than having zeros and one, you have really quantum states to store your information. And therefore, since your system is naturally embedded in quantum state, it naturally has the memory and the ability to deal with the conceived complicacies of a quantum problem. Now, there is an interesting course on quantum computing in the University of Trento, given by Professor Hauke, who's a world expert. And if you get excited about quantum mechanics, I would strongly recommend you to go and take this course. From the technical point of view, you will be equipped to follow it with just the amount of quantum mechanics you learned from this course. And this is one of those courses that is likely to be useful for you in the future, because quantum computing is now growing a little bit like the Moore's law when classical computers were booming from the 70s till, let's say, now, or maybe a decade ago. So I think quantum computing is a very important perspective for the future, and you have a chance to learn about that in Trento, taking that into account. Part of my research now is being devoted to use quantum computing for biological applications. So let's go back to us. We have a quantum wave function, and now let me concentrate on specific quantum systems. So we're going to talk about what is called quantum degenerate system. And in this context, quantum degenerate means to the fact, it refers to the fact that it is a quantum system made of identical particles. Okay, so indistinguishable particle. So if you think about it, a system of indistinguishable particles, I try to make my balls here as I draw as indistinguishable as I can. So now, if I were a perfect drawer, so to say, or if I use my computer to draw them, then clearly, if I ask you to close your eyes and I swap two particles, for instance, this with this, and then I say, okay, now open your eyes. Do you note anything different? You wouldn't be able to note any difference because all the dots are equal. So the wave function must be some sort of, there must be some intrinsic invariance or symmetry, as you know. Symmetry is the normal word that physicists use to describe the fact that a system might be left invariant by some manipulation. For instance, a sphere has a spherical symmetry, because if I take a sphere, now imagine a sphere like this. This is, and imagine to have it painted in black, perfect black. Then the moment I rotate the sphere, you would not be able to notice that I'm rotating the sphere, because you would not be able to see the stripes. You would see just black, no reflection, nothing. And the sphere has a shape that is left invariant by any rotation. However, the stripe of this basketball here are breaking the symmetry, because allow you to distinguish states that are connected by this rotation transformation. So a quantum system with a symmetry under exchange of particles is completely left invariant by exchange identical particle. But if you have something that is distinguishing between the particles, for instance, mass, then you will be able to see which particle is which, right? Now, I'm spending a good deal of time in discussing symmetries, because this is the point where in quantum mechanics, a magic happens. And if you want, this is arguably the last big law of quantum mechanics, fundamental law of quantum mechanics, that we didn't discuss yet, and should be somehow added to those we introduced previously in this course. The reason we didn't introduce this law at that point is that we were not talking about many particle systems. right? So was so what is this new law that is fundamental and shapes the structure of matter, especially of condensed matter, such as, you know, chemistry or materials or anything like that, is the so-called spin statistics theorem. Now, as the same name is saying, this is a theorem, but this is, boy, a very complicated theorem. And not very few theoretical physicists in their education get to know the proof of this theorem. Basically, only a minor branch of theoretical physics, they go into very mathematical fundamental aspects. So certainly it's not our goal in this course to derive the proof of this theorem, to expose you to the proof of this theorem. It requires quantum relativistic tools. But I can certainly do what most physicists do and state the implication of this theorem, or if you want, the thesis of this theorem. So the wave function of many particles, so the quantum many wave function, which we will denote as psi1 and 1, the collection of quantum numbers of particle 1 through xn and n. This wave function has important symmetries, is symmetric. You know, if these particles, identical particles, these are identical particles, and if they are fermions or bosons, they behave very differently. The wave function behaves very differently. The wave function is symmetric. Ah, pardon. One second, please. I was saying the wave function is a collection of identical particle. Is if the identical particles are fermions, or if the identical particles are boson, so spin 1/2, spin 3/2, spin 5/2, or whatever, and this is spin 0, spin 1, spin 2, blah, blah, blah. Well, if you have a system of identical boson, the wave function is symmetric under exchange of identical particles, which means basically that psi x1. Now let me call, this is the collection of all the continuum. So x is a continuum quantum number, and n is a discrete quantum number. Let me call simply capital X a vector that collects all these quantum numbers. So all the discrete and all the continuum quantum numbers, just for a matter of notation. So the wave function for boson is symmetric under exchange of any pairs of particles. For instance, psi2, psi1, psi-n. Symmetric means that you can take any of these particles, swap them, and put where in the position where you had the quantum numbers of particle 1. In this particular example, I put the quantum numbers of particle 2. And where there were quantum numbers of particle 2, I put the quantum numbers of particle 1. And the wave function is left unchanged. That's what you would expect, right? I mean, if I have identical particle and the system doesn't know how to distinguish them, when clearly the probability of this configuration and the probability in which this particle is swapped with this, how can the system know they're identical? The probability must be the same, right? So this part of the theorem is what you expect from our intuition. Remember, we build our intuition in the classical world. And in the classical world, that is happening. For instance, if I tell you what is the probability that I throw this coin, these are two identical coins. Can you see them? Oops. Two identical, 2 euro cents coin. And I'm asking myself in a classical problem, what's the probability that I get this coin in this position and this coin in this position after I throw them? Okay, maybe I can compute them. Then clearly the probability to find this configuration must be identical given the identical initial condition, because the two coins are completely identical. So how can nature distinguish between them if they are identical? So it can only be the same probability. So this part of the theorem that says take a quantum antibody particle, let all the identical particles be boson. If you interchange any pair of this wave function of these particles, and you look at the new wave function, it must be the same wave function. But the big surprise comes when the particles are not boson. Oh, sorry. When they are fermions. Because if you have a wave function of fermions, and you interchange two particles, and here as an example, I'm taking particle 1 and particle 2, but I could take any possible combination. Well, magically and mysteriously, the wave function changes sign. Now, this is still not, it looks like nature, through the sign of the wave function, knows. Nature knows that you're changing the sign, that you're swapping the particles, even if the particles are identical. And it lets you know that she knows. I'm giving the she to nature, and lets you know that she knows by putting a sign in the new wave function that you obtain after swapping to Fermi. I mean, at the moment, it might not be particularly exciting. This might look like a mathematical results with very little implication. It turns out it has enormous, gigantic, huge implications. And I'm gonna elaborate on that in a moment. For instance, you may say, well, come on, we know that all that we can measure are actually probabilities. So if the wave function changes sign, I'm going to take the square modulus in the end. So this would be a not noticeable change in the system. Now, that might be an argument you might be tempted to have. How do I know that a wave function has changed sign if only square modulus of wave functions are relevant? Well, it is not quite so. In fact, the wave functions of fermions and bosons is in fact radically different. Sorry, I have to take this. Is in fact radically different. Why? Well, let's suppose the wave function has two entries, two identical particles. It's made of identical particles. Suppose that two of these particles have exactly the same quantum numbers. So for instance, I have x1, x2, x3, xn. And let's suppose that two identical particles are exactly in the same quantum state. Why not? I have two particles sitting onto each other, same position, same spin, and everything. Well, that means, say, let me call it Y. By this, I mean all these quantum numbers are the same, and I'm calling them Y. Right. Now, if I interchange particle 2 with particle 3, I would get x1, x3, x2, xn with a negative sign. But I'm interchanging identical particles, so I should write y and y, because x2 is equal to y and x3 is equal to y. Now, the only way, and I got the same function, the function is left unchanged by this symmetry up to a sign. So the only solution to the equation x is equal to minus x, or psi is equal to minus psi in this case, is psi is equal to 0. For any psi different from 0, you cannot be the negative of yourself. So the wave function cannot, if you have a system of fermions, two fermions can never be found in the same quantum state. Two identical fermion cannot be in the same quantum state. What do I mean by same quantum state? Have identical quantum numbers. Quantum numbers. This fundamental properties of fermions is called Pauli exclusion principle. It's called a principle because it was postulated before it was demonstrated. Sorry, my son is coming. A movie for my students. It's called an exclusion principle because it was conceived before it was actually demonstrated from the spin statistic theorem. Now, the Pauli exclusion principle tells you something deeply, radically important for the quantum mechanical problems. Suppose we take now a very simple quantum mechanical problem. We take a number of particles, a number of bosons, and we put that into a one-dimensional harmonic potential. What is the lowest energy state of this system? And clearly is one in which my n particles are all in the ground state, because if they don't interact with each other, remember, if they don't interact with each other, the energy will be the sum of my energies, and the wave function will be the product of single particle wave function so the lowest energy is when all the energies will be the ground state. Fine, no big surprise. If I take many balls and I put them into a jar, if I wait long enough, their energy, they start bouncing, and then after a while they dissipate their energy by making noise and making friction with the air. Eventually they lose all the energy. They will be found in the ground state, and the ground state is where all the balls are at the bottom of the jar. So in a quantum system, the equivalence of that, all the particles will go down to the ground state. The ground state is not going to be exactly the bottom of the jar. There will be a 0-point energy. We discussed that. It's going to be 1/2 h bar omega. Fine. But in the end, from the essence of it is everybody in the ground state is the result of dissipating away all your initial energy. However, if you have a system of fermions, something changes radically. Indeed, I have my ground state, first steady state, second steady state. Now I'm gonna need more levels, because even if I have a system of particle, of course, the first particle can go into the ground state, and say this is our fermions. So the simplest fermions are electrons. So let's put these electrons will have spin off. Now, if I have a second electron, I can put it in the ground state only as long as I change the spin, because if I did not change the spin, then I would have two fermions exactly in the same ground state, in the same quantum state, and I would contradict the Pauli principle. And when I put the second particle, the third particle, I can no longer put it in the ground state because there's no room for them. I have already two particles, one spin up, one spin down. All the other quantum numbers are the same ground state. So there's no room for that. I have to put it in the first excited state. So I can accommodate the second particle here, and I can only fill up in pairs the energy levels. So the ground state energy of 4 fermions will be h bar omega. So suppose there are 4, if there are 4 bosons in a harmonic trap, the ground state energy will be 4 times h bar omega half. So it's going to be 2 h bar omega. If there are 4 fermions, the ground state will be, I can put out of 2 particles, h bar half omega, and then the next 2 particles will have to have 2 times h bar omega half plus h bar omega. That's the first excited state. So this is going to be h bar omega plus h bar omega plus 2 h bar omega. It's going to be 6 h bar omega. Okay, it's official. I can now count 4 h bar omega. So you see, you have double energy. Well, obviously, it's even clear for the picture. I have double energy with respect to the boson system, and the energy keeps on growing if I add more and more particles. So if I have, n particles, then I will have to put in pairs. So eventually, the energy of my system will grow simply because I have identical bosons. So the Pauli exclusion principle has tremendous implications in quantum mechanics. And I want to conclude this lecture by making a point. Remember, and by this simple rule, you can actually understand basically all of atomic structures, at least at the qualitative level. What do I mean? Remember, when we studied the hydrogen atom, we have a single electron and a proton. The electron, of course, is distinguished by the proton because they have different masses and different charge. Now, and we worked out all the mathematical solutions, and we discovered that there were S states, P states, D states. There were a number of S states. For instance, if I remember well, there was S1, or actually S1, S2, notation starting from 1. There was P1 and blah, blah, blah. Now, What happens now if I have more than one electrons circulating around? Of course, no longer a proton, but a nucleus with a given charge Z. Right, this is the nuclear quantum number. Now, you see, what happens now is that you can no longer, the ground state of this, of course, there would be, the wave function of this many-body system will change, will not be the same as that of n individual electron. And this is because of basically two main differences. First of all, a trivial difference. Electron will interact among themselves. They feel the mutual repulsion. So this will change the shape of the wave function because of the Coulombic interaction among the electrons. This is something we could have guessed even at the level of classical mechanics. But on top of that, and perhaps much more importantly, there is a fundamental difference that comes precisely for the quantum nature of electrons and for the fermionic nature of electrons that concerns what we have just finished discussing. Electrons are fermions. So I can imagine that, maybe the fact that there are many electrons results in changing the details of the wave function. Maybe the electrons experiences an overall effect of all the others, changing a little bit the wave function, but more or less the ordering of the state, S1, S2, P1, P2, blah, 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 is not that different. So I can still use this ordering that I discussed before. This ordering here to organize the states of any multi-electron atom. But now you see, what is the energy? What is the energy of an n-electron atom? Look down the periodic table, and then clearly, let me draw a diagram. Well, of course, I can put an electron here, and I get the hydrogen atom. Or I can take two electrons in the ground state, and I get a helium atom. Now, the next state will have a higher energy because the next two electrons have to go in the S2 state. And then, if I have more electrons, and so I'm going forward in the periodic table, I have to populate a p state. And how many electrons can I put in a p state? Now, the p state has 1 unit of angular momentum, which means that there are 3 states for the m quantum number, +1, 0, and -1. So in order to have a number of electrons that don't have, the maximum number of electrons that don't have the same, such that the 2 electrons don't have the same quantum numbers, is actually 6 in this case. So that means to say that I can accommodate this, 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 and this, and this. So any of these 6 states would be in a p state. So this is for m equal 1, m equals 0, m equals -1. So if you use these simple rules, you can discover that you can basically reconstruct all the properties, the qualitative structure of the Mendeleev table. Discovering that anytime you have a p state, then you have a system that is, from a certain point of view, different from the previous one, but it has the same number of electrons in the last shell. So these are called shells. And if you have any concept in chemistry, you remember them from chemistry, because the electrons organize in shell because of the exclusion principle. Now, probably when you discussed the exclusion principle in your previous chemistry education, you were not exposed to the deep quantum origin of it, the antisymmetry of the wave functions for fermionic systems. Now, I guess you have, And so basically, you know that the Pauli exclusion principle is what you need to understand the Mendeleev table from an atomic point of view. And this is the way you build a Mendeleev table. So you see the implication of having quantum spin statistics theorem are deep because they basically shape the structure of atoms and therefore ultimately the structure of matter as we know it. Okay, thank you very much for taking this lecture, and I'll see you hopefully soon